Okay, we're cooking with grease now. Hey, hello everyone to our meeting for October 20th. I'll just start with our schedule. So we had a guest speaker last time. I'm guessing everyone here liked the guest speaker. Certainly you, as you were a speaker yourself. But yeah, if everyone liked it, I think we should try and get like more speaking events. Maybe we can sneak one in before the end of the semester, like late November. I think I actually want to see if we can do a joint one between us and AI Club here, because I have a talk in mind that it's basically overlapping between two of us. Maybe even get SC Club as well, because it kind of overlaps all three. Because I just went to a conference and gave a talk that was machine learning for software engineering, so it kind of like hits everyone. So we could probably do a big kind of group talk. And today we'll be doing exploratory data analysis. And then I'm really excited for the coming weeks because we're going to start like a kind of like an algorithm sequence. And I think that's really the fun part of all this. So first, I want to kind of give everyone time to discuss the data set. I hope everyone looked at it because everyone liked the talk, and then you got the data set off of it. So kind of some leading questions. So first, like, what was your approach? What did you discover, and what challenges did you face? So how many people actually took a stab at this data? Anyone? Bueller. Okay, we got one. So and especially because you talked about it, so and you've worked on it for however many years. 2 years. So yeah, so why don't you answer these questions? What's your
approach?
Yeah.
Well, we get a lot of data in NGAFID from so many institutions. I think it's like 150 last I counted. So the approach is, well, just keep it organized.
Yeah, keep it organized.
We store, at least for the way we keep things accessible to the user, it's all stored as a blob database, right? So our approach to dealing with it is, if I'm doing something like classification tasks, which I'm kind of in the process of doing right now, we just export it as a CSV.
Right.
But the thing is, there's about, I don't know how many columns.
It was a huge data set. It was like 3 gigs compressed.
Oh, yeah.
Like, like it was like several thousand flights with second by second data collection from 23 sensors.
And what you'll notice is that there's a million, like not a million, but a lot of different parameters. So in the CSV file in the header, you'll get like stuff from not only like what's going on outside the aircraft, but also going on like within the aircraft's internals too. And so for the maintenance stuff, for Hong's work with the predictive maintenance, I think that what you really want to look at is more of the like what's going on inside the aircraft, whereas what I'm doing is kind of more how the aircraft's flying, things like that. So it can be challenging to know what every parameter means. I think that's probably the most challenging thing.
It was like 23 sensors, right? Or something like that.
It can be more.
It can be more, but it was like you had like flights before like a maintenance event and flights after, and you could kind of predict, or you're trying to predict when maintenance would happen by seeing the before and after, which is a hard problem, but I've seen it before. Like when I was working at Los Alamos over the summer, these people were trying to do the exact same thing except with a particle accelerator, because that's kind of a very expensive thing to run. And if it breaks while you're running it, your data is garbage. So they wanted to use a bunch of like sensory data to try and predict when it's going to break, so they can try and fix it before they actually run it. Because it was like something tens of $1,000s per like run. And obviously for aircraft, you want to try to predict when something's going to break, because that could be bad.
So across all of our aircraft right now, this is actually just a subset. So this is a more of a concentrated instance that we have. There's about 117 different columns that we have across.
So high dimension feature space.
That's across. Hang on, let me tell you how many different aircraft. That's across 3 different aircraft. So yeah.
It's a high. Yeah.
However, I will say that that's 117, but I think maybe 5 or 6 of them are calculated after the fact. So for my presentation last week with the stall index, I could calculate after the fact.
It's an engineered feature.
It's an engineered feature, but
Yeah.
like, put into the database app.
So yeah, what discoveries have you made in your time working with this?
Oh man, but there's made a lot of discoveries. I think. Oh man, I think one of the biggest discoveries I made is that there's a lot that can be done with this.
Yes.
So, like one of the things I'm working on right now is trying to classify the different maneuvers that pilots perform.
Because Travis mentioned that some of the data was just taken from people who do like aerobatic, like flight stuff.
Yeah, there's that, but also every flight school that, well, the ones I work with at least, they all have training programs where they're supposed to go out and do things like stall the aircraft, use control, so they can
Yeah.
practice recovering.
Yeah.
Right. And there's many different ways they can do that.
Yeah, but that's hard if you try to take like an anomaly detection approach to the data. Because if you're trying to figure
It's
out
too
something,
general.
if something's wrong based off sensor data, well, they're doing wrong things on purpose.
Yeah, you
Yeah.
definitely, to look at this data, you need to know a little bit about aviation, like
Yeah.
airspeed, altitude, how it works.
Domain
vertical speed.
knowledge. Yeah.
Yeah, definitely. Especially if you want to do like anomaly detection, because you can't. It's hard to do generalized anomaly detection
Mhm.
because of how specific the parameters are and what
Mhm.
range they should be in.
Yeah.
So, like for instance, airspeed on a Cessna 172, which is the small aircraft that we usually deal with, it could be anywhere from 40 to 120 knots in the air.
Yeah.
Whereas on say if you're on a plane
Like a Boeing, like
like an
Airbus, like
A320,
yeah.
an A320 will fly maybe at 335 knots.
Yeah.
So you really have to. There's a lot of different.
Yeah. This was a much more challenging data set than I thought it was going to give us. And I only anticipated to like be a week, but people have been working on this for years. So I wasn't expecting anyone to like get anything conclusive, but maybe just try and take a stab at it. I'm like, oh, this is real data and it's all ugly. And how do you deal with that?
I think one thing that would be cool, what would be cool to do is do some data visualization first.
Yeah.
So plot, maybe airspeed, IAS is one of them. Plot. I think if you want to look at aircraft parameters, look at the volt meter, the volt A, volt B, I think. Those are good ones to look at, and you can kind of see a graph over time. I think that's the best thing to do first.
Because it's all time series data, right?
Yeah.
Because it's all sensory.
Okay. I would also say like using the NGAFID itself, I think we could probably get this club access to a data set on the NGAFID so you can look at our features as well.
Yeah.
But right now, there's something going on with our machine where it just stopped working last night, so we can't use our data set, unfortunately. Yeah. I'm in the middle of arguing with GCCIS right now about all that.
Yeah. Well, those who that didn't look at the data, I encourage you to just at least try to explore it on your own, so you get to see what real world, very messy, not contrived data for our classes look like, because that's just a good exercise. But to start, I wanted to start this meeting with like a scenario, because this is going to play really well into what we're trying to do. So let's say a junior scientist is given labeled data and they are tasked to do some type of classification. So they have good knowledge of the machine learning pipeline and they understand that the data can be turned into features that map to the output. So it's kind of like your classic like machine learning problem. So what they do is they do a little data cleaning and normalization and input their features and labels into their favorite classifier and get results until upon testing, they are predicting very poorly and start to feverishly swap models, but find no models predicting well. So at the next meeting with their manager, they share the results and are asked why their classifier is not working, but they can't explain why. So has anyone else done something like this? I know I have, where you are just given data and I just kind of like split it up and just run it through a model. I don't really think about it. It's kind of like blindly shoot it. So for this, where did they go wrong and what did they miss? Why did this turn to a disaster for this junior data scientist? Yeah, so there's some bias in the data they didn't take into account. Yeah, the data could just be like, you can't classify with this data, whoever collected it, like they weren't thinking, or it's just like the classification is impossible. Yeah, so they weren't even thinking about feature selection. They just kind of fed everything to it, yeah, without thinking.
They didn't fine-tune the parameter model.
Yeah, they didn't like focus on it. They didn't actually like work through their model. Yeah, yeah, those are all good responses. So now we're going to go into exploratory data analysis. And I think the mantra for like any modeling is going to be garbage in, garbage out. If there was a 10 commandments of data science, I think this would be like the first one. And if you're a data scientist, maybe like get this tattooed on yourself, because like this is like the quintessential like problem when you're doing any type of modeling, any type of analysis. Garbage in, garbage out. If you don't understand your data, and especially if you don't understand the model, you're plugging something you don't understand into something you don't understand and praying for good results. But when you don't get it, you have no idea why. And I think the whole point of exploratory data analysis is to understand your data before you even do anything with it. And honestly, I think there's kind of a plague of like bad data science where people kind of skip this and go straight to the modeling. They're like, okay, we got the data. We're not going to do anything with it. We're not going to like see like what the data is like. We're just going to plug into a model and hope that we get the right answer, which hint, you can't do most of the time. You can get lucky sometimes, or maybe you'll get a model that, you know, happens to actually do what you think it's going to do. But you should really be sure on what it's going to do before you even feed data into it. So what is exploratory data analysis? IBM defines exploratory data analysis mainly by you look at the data before making any assumptions. So you kind of, you know, do your preliminary exploration. You want to better understand patterns within the data and then find interesting relations among the variables. And that's exactly what you should do. Like the first thing you do when a data set hits you is not, you know, go straight to the, you know, train test split or just like normalize it and go on. You should look at the summary statistics. You should visualize the trends and the distributions, and you should be finding patterns and correlations in your data if they exist. And within this, there's some clustering and there's principal component analysis, which I think we're going to go over in a couple weeks when we go into clustering. We'll do both of these, but I just wanted to let you guys know that within exploratory data analysis, a lot of people do clustering or they do some type of component analysis to like understand their data better. And this is kind of something hard to show statically within slides. So I'm going to go right into a tutorial for this because that's the kind of the best way to go about doing this. So we're going to be using the housing data set like we did before for our, it was data cleaning and feature engineering. So you're going to recognize this data set. And honestly, Tolu went over a lot of EDA when he did it, but I'm kind of going to go more into like a granular way. I should probably drop this into the Discord, but it's pretty short. This meeting is kind of very variable length depending on how much we had to discuss for the data set at the beginning. But I think this will be still insightful, but yeah, I'll drop this after. So first, you know, we got to load in our data as always, you know, look and see. I think everything's ran, but look and see at our summary statistics. For some reason, you know, we would just default to like, you know, pandas.describe method. But for some reason it does mean, but not median. And I think when you're looking like at the statistics for some distribution of data, I think knowing both is good because that'll give you some sort of information about how the data is skewed. Because if the mean and the median are off of each other, you know that you're going to have some skew in your data. So like, let's say here for like total rooms, the mean looks to be significantly higher than the median. So that's, let's see what kind of skew is that. I got to think about that. Let's see, the means here, it's higher. So yeah, there's some type of skew in the data. And so just looking at the surface level summary statistics, especially things like the mean, the median, and the standard deviation, will give you a very good idea of like how your data is kind of spread out, how like well behaved it is. But really, you need to go into like the data visualization. I think we've seen these plots before, but I'll go over them. So like we see everything kind of well behaved, kind of that normal, or I'd say kind of like a Poissonian distribution, which is kind of just a normal distribution slid over, except for we have a few things like the longitude and the latitude of the houses that look to be kind of bimodal. So that's something to look into, like, okay, this isn't all normally distributed data, and the housing median age is also kind of weird. So at first glance, we can always already see that there are parts of our data set that aren't, very well behaved, or that they're at least not representing some type of normal distribution we'd expect. So this is already a red flag that you shouldn't just plug this data into a model and hope for the best, because you're going to have some weird behavior in there. So going on, we can use the kind of the classic like correlation map or like the heat map. And for the purpose of this tutorial, I would like to predict the median home value. So like, can I take the features we have and kind of predict, or like kind of do a regression towards what is this house going to be valued at? And we see, like, especially at this column, there isn't a ton of things that are correlating directly with the value of the home. The highest thing that's, correlating with it is going to be the median income. So that's probably going to be a significant feature if those things are highly correlated. That's a very good, predictor that we should look at. Other things are not so correlated. Maybe with the latitude and longitude, there's some slight inverse correlation, or they're negatively correlated with the median house value. And then we get like some pretty intuitive ones, like just looking at it, like the total rooms and the total bedrooms are, well correlated, which makes good sense, because if you have more bedrooms, you will have more rooms. And then there's some weird correlations, like the latitude and longitude seem to be extremely negatively correlated. So that's something we can look into. So even, before touching any sort of model, we're just looking at the behavior of the data to see what things will help us later on in our analysis and our modeling. So if we go on to look at these correlations, like total rooms and bedrooms are highly correlated, as we can see here. I'm like, okay, yeah, that makes good sense for, like, if you add a bedroom on, you have to, by definition, add a room on. And looking at the median income and the median house values, we see strong correlation up here until we hit this wall, which I think we discussed last time we looked at this, that the median house value is kind of capped. So anything past that looks to be 500,000 is just set at 500,000. So there's a little bit of, weird behavior in the data, kind of artificially instilled, which is a good thing we know now, because we should take that into account when we're modeling. Because if there's something that should be out here, but it's not, and it looks like there's only 2 of our features are capped, but the rest of them aren't. So something like median income could reflect a median house value that doesn't exist in our data, which is obviously going to be a problem for predictive power, because there could be like a very good trend between median income and median house value. Like maybe if this wasn't capped, it'd be like almost perfectly correlated, but because there is a cap, it kind of like breaks that symmetry. And that's something we need to think about especially when we assess the accuracy of our modeling and how we approach our modeling. And so there's other things we can do. Like, let's say we can look at the location of a house versus, I think I took the median house value like mean. So like the average mean value of the house, depending on where it is. We can see some trends in here, but really, we're just searching around the data. That's exactly why it's called exploratory data analysis, because you don't know what you're going to find until you go looking. But what I thought was really fun to look at is we saw the high negative correlation between longitude and latitude. And it just happens to be, that's because of how California, the state that this data is taken, is laid out. So there's not an actual reason behind that, except for, geography. It's like, yeah, it happens that California is in a shape where the longitude and latitude will be inversely correlated. So now we found a relation that isn't significant, but it is there, and we found it in our analysis, but we kind of got to like think through it and explore it more, because if we could be like, I wonder what's happening there. It's like, oh, that's just how the shape it is, um, but there's more we can do. I think we saw a similar plot a couple weeks ago, but I plotted latitude and longitude and colored the dots with the median housing value. So now we can see clear clusters of like, okay, the very expensive houses are near the coast. This should be ocean, but I'm not fancy like Tolu and plotting this over an actual map of California. So you can pretty well visualize, what it looks like. So this is all coastal regions. And then as you go inland, it seems that the median housing value goes down, except there's some, there's some random guy with a really expensive house kind of, on the other side, but
That's where Tahoe is.
Tahoe, okay, yeah. And then, I think there was a lake here or something, but yeah, Home Springs, but that's the value of plotting it over a map, is you can actually map this to where things are. So now I'm thinking we actually have a pretty good like clustering naturally in our data. Like we might not need all of our features to, do predictions on our housing values, because it seems like they kind of lay themselves out for us to begin with. So now I'm going into, okay, how do I actually predict house values? And we'll go into regression in a couple weeks, but just, I guess, accept that there are models that can take in features and predict values or fit a line. And so here we want to use our features and try to, predict what the housing value is. So first, I'm going to run a full model. So literally everything in our feature space, just give it everything, tell it to, predict the median house value and just let it go. And it looks like we get an accuracy of around 93, 94%. 60, sorry, 60. Yeah, it's been a long day. So not too good, but for the sake of this exercise, we're just going to compare two models together. Yeah, and then so now looking at how the data behaves, I'm just going to select features that I think or look like they can map on to what we're looking for, because we saw that the median income highly correlated with our median housing value, and it looks like everything is very well clustered by its longitude and latitude or its position. So I just gave it 3 features instead of the full feature set, and lo and behold, we are actually predicting better with less information. So you can't just blindly go at it and just take all the information and shove it into a model and expect it to do well. If you actually think about the features and how they're behaving and select them like accordingly and run it through a model, you will get better performance. And that's really the kind of the crux of why you should do EDA. I think last time we saw like 60% of a data scientist's job is like looking at cleaning the data and like engineering features and making it work. But EDA and data cleaning kind of work hand in hand, because how the data behaves will kind of guide you towards how it should be cleaned and what features you can pull out or what features you can engineer. And unfortunately, that's all I have for you today, because I was wondering if people were going to deal with Travis's data set, but that's okay. Does anyone have any questions or comments or concerns with this?
I have a question.
Yeah.
Where's some like exploratory data analysis techniques that you could do for image data?
For
Maybe
image
object
data.
detection.
Yeah, object detection is going to be like what I think this is more with like vision transformers, but you can pick out like do edge detection first, or do like like image segmentation, like kind of like what important artifacts are within the image that some type of like image recognition model would look at. And there's a lot of work into that actually. A lot of it is kind of going backwards though. Like you have a model do like image recognition, and then you find the feature importance within like the image itself and look at where your model paid the most attention. But I know there are some processing techniques that people use before they give it to the model. Like you can do like edge sharpening, like you can like run filters over your image to like make, the edges on everything, like especially with like facial recognition, people a lot of times will do like edge sharpening so the person's features are more pronounced. But yeah, that is an interesting question. I'd have to think about it more. Because like yeah. Yeah, I think, yeah, that's right.
It will be like heavily blue color. So maybe you process that in different ways. Suppose you want to find where the oil split on photo. So maybe the color information there is more important than other obligated market.
Yeah. Actually, yeah, that sparks my memory about something. When I looked at a machine vision problem, the first thing they did, they looked at a histogram of all of the color, all the RGB values. Yeah, because yeah, you can. Yeah, and you can see the color layout, because like if it's too weighted towards one, you could say that's a significant feature when it's not. And depending on what you're doing, I think there are some classifiers that can classify solely based off of like the color distributions. Yeah. 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 It's a dog, green bat. Yeah. That's good. Yeah. I think maybe next semester we should have a whole like machine vision or like image processing like day. I think that'd be fun. Yeah. Any other questions or queries like that? That was a good question. Thank you. Yeah. Yeah. I mean,
Yeah, I guess you probably do that anyway.
yeah, you'd probably do that anyway.
Yeah.
Yeah. So how are we doing on time? Yeah, okay, I can give you guys some time back, so you can go on with your lives. Okay, I will stop sharing.